So we're going to carry on with our modelling curves, and we're going to look at case 2. We looked at case 1 in video 1, and in case 2 we know that it is slightly different because the second variable t is now in the power. The table shows the size of a population of house sparrows from 1980 to 2005. The number of years since 1980 is the variable t, and that's given at 0, 5, 10, 15, 20 and 25. And the population of house sparrows, p, you can see has decreased over the 25 years from 25,000 down to 12,000. There is a third column, a third row, and the question is, do we need to work out log to the base 10 of t, or log to the base 10 of p, or both? So we're going to rearrange our equation using our log rules in the same way as we did in case 1. So I'm going to take log to the base 10 of p on the left hand side and do log to the base 10 on the right hand side of a times 10 to the minus kt. That needs to go in brackets because we're logging the whole of the right hand side. So the left hand side, log to the base 10 of p, equals, I'm going to use my log rules and make it log to the base 10 of a plus log to the base 10 of 10 to the minus kt. We're now going to use our log rules, and this power is going to be brought down to the front. So log to the base 10 of p equals log to the base 10 of a minus kt log to the base 10 of 10. Now we know that log to the base 10 of 10 is 1. So our next line, we can say that we have log to the base 10 of p equals, and I'm going to rearrange this slightly so that I have minus kt plus log to the base 10 of a. And as we did last time, we're now going to compare this to y equals mx plus c. Our variables are log to the base 10 of p, that's going to be y, so y equals log to the base 10 of p, and x is going to be t. We then know that the gradient m is going to be negative k, and we know that the constant c is going to be log to the base 10 of a. So that answers the question of what we need to find in our third row. We don't need to log t because x is just t, but we do need to do log to the base 10 of p. And we need to find these values. So you can pause this video and work out the different values. So these are the values. Hopefully you got these correctly. They're all given to 2 decimal places. So we need to plot log to the base 10 of p against t. And we're going to plot the points 0, 4.40, 5, 4.34, 10, 4.27, 15, 4.21, 20, 4.13, and 25, 4.08. So I've plotted these points, and you can see that they make a straight line. There's a negative gradient, which is no surprise because the population of house sparrows was decreasing, and we're going to look to do a line of best fit. So if I draw in a line of best fit and try and make it so that there's a sort of even amount of space on one side and the other, so we'll put it there. And we need to find the gradient and the y-intercept of this line. So what we have plotted here is we have plotted the points log to the base 10 of p, so log to the base 10 of p equals minus kt plus log to the base 10 of a. So we know that our gradient, I'll write this up here, so m equals minus k, and we're going to find our gradient, and we know that c equals log to the base 10 of a. So we're now going to find the gradient. I've drawn in the triangle to help us to do this, and we can see that the gradient is going to be the change in y, which is 4.4 minus 4.14, and that's going to be over 0 minus 20, and so we get a gradient of 0.26 over 20, and that's negative, and that's negative 0.013. This is equal to negative k, so k equals 0.013. The y-intercept is at 4.4, and so log to the base 10 of a equals 4.4, and so a equals 10 to the 4.4, and a equals 25,120 to 4 significant figures. The value that we were given in the table at the beginning was a start value of 25,000. That's the population of the sparrows in 1980, which is the same value to 2 significant figures. So we can now substitute these back into our original equation, which was p equals a times 10 to the minus kt, and we get p equals 25,120 times 10 to the minus 0.013 t. So what we've done is we have used the modelling curve to find a linear relationship between t and log to the base 10 of p, and we have used that to find our constants k and a, and so we can now have a final equation between p and t. We could use this to find the population at certain times, or to find the time of a certain population. So what conclusions can we draw? Well, in both videos, one and this video, we have used 2 different case studies. The first case 1 was p equals a t to the power b, and the second one was p equals a times 10 to the power of minus kt. And we know that the key difference is the positioning of the variable t, which is either as the part of the base or is as part of the power. And the positioning of the second variable is very important because that dictates which logarithms we need to use. So in both cases, we take the logarithm of both sides of the equation. We usually use log to the base 10, but it is possible to use ln, the natural logarithm. The new equations are then rearranged using the laws of logarithms so that they're in the format y equals mx plus c. So in case 1, we ended up with log to the base 10 of p equals b log to the base 10 of t plus log to the base 10 of a. What this means is that we had that y equals log to the base 10 of p, that x was log to the base 10 of t, that m was b, and that c was log to the base 10 of a. And the linear graph that we drew, we were plotting log to the base 10 of p against log to the base 10 of t. In case 2, when we rearranged, we had log to the base 10 of p equals minus kt plus log to the base 10 of a. So in this case, we had that y equals log to the base 10 of p. We had that x equals t. The gradient m was negative k, and the y-intercept c was log to the base 10 of a. The linear graph that we plotted with that, we were plotting log to the base 10 of p against t. So if you have an initial equation where the t is the power, then x is just t. Whereas if t is the base, then you are going to have that x is log to the base 10 of t. At the bottom of the page, we've got a general conclusion. In both cases, the points are plotted and the line of best fit is drawn. The gradient and the y-intercept of the line of best fit can be found, and these values can be used to find the constants, just like we did before. The constants can then be put back into the initial equation, and you can find a relationship between your two variables, and you have done this using a modelling of your curves into a linear graph.